everyone. Pleasure to introduce Jakob Robnik, who is visiting us this week. So Jakob is a fourth-year PhD student at UC Berkeley. He's from Slovenia, so he did his undergrad at the University of Ljubljana, and then he did a master's at ETH, and now he's at Berkeley. And he's an expert on Bayesian statistics, data analysis, building algorithms, and he will tell us all about this.
Thank you, Maria, for inviting me and for the hospitality. Okay, yeah, so I will talk about, we have some time series data, and we would like to detect some periodic signal in that data, and I will talk about how to assess statistical significance of this signal. So, the generic problem that we have, okay, maybe we have some time series data, maybe this is the magnitude of the quasar as a function of time. And then we detect something like this. We find that it kind of looks periodic, the fits look good. But then we would like to decide whether this is statistically significant and assign the number of sigma to that. And then tell if this is some genuine signal, or are we just looking at some schematics in the data? And the method that we have developed for doing just this is, we call it the null signal templates. It's a data-driven method, and it can be applied to a wide variety of problems. Particularly, I will talk about these first two applications because we have already worked on these two. The first is search for supermassive black hole binaries, and the second is search for exoplanet transits. But it can be applied more broadly, for example, to radial velocity exoplanets, or to search for exomoons, or even to non-periodic signals like gravitational wave mergers. So the plan is I will start with this first application and introduce it, then show how the null signal templates come in, and then we'll move to the second application. So the general idea is we would like to detect supermassive black hole binaries. We know from numerical simulations that this system exhibits, so it influences the accretion disk around it and influences it to change brightness over time. So these are numerical simulations for how brightness of the quasar changes as a function of time, and we can see these periodic variations. And this period here is the redshifted period, orbital period of this binary system. So if you detect something like this is a strong signature of supermassive black hole binaries. So our strategy will be, we will take some quasar catalog, specifically in this work we took PTF data, and then because numerical simulations are quite expensive, so it's hard to generate templates like that, we will simply approximate this with a sinusoid. This is what is typically done in this kind of analysis. And then we will model the noise with a damped random walk, which is also a standard assumption. So then we would like to analyze the data and see if this hypothesis that there is periodic signal is above the hypothesis that there is just damped random walk. So to do this, there are basically two main schools of thoughts how to approach this. The first is the frequentist approach. So here one designs some test statistic, which is a function that takes in the data and spits out a number, and this number is large where there is high evidence for the signal and low when there is only noise. And for example, for this you can take long scarlet periodogram score, or even better, take into account also that the noise is damped random walk and improve on that. Then given this test statistic, you compute it on the given data, and then you compare it to the distribution that this test statistic would have if there was no data. So you generate simulations with no data, you look at the distribution of this test statistic that you get, and then you look then you compute the probability of seeing a larger test statistic if there was no signal. This is called p-value. And if this is very low, then then the no data hypothesis does not seem very likely, and so you confirm your signal. Typically, for example, if p-value is below 1%, you can claim a discovery. On the other hand, there is the Bayesian approach. In the Bayesian approach, you look at this Bayes factor, which is the ratio of these probabilities of the data given if there was signal compared to the probability of the data if there was no signal. So the larger this ratio, the more likely that the signal hypothesis seems. And then you confirm your signal if this base factor is very high, for example, larger than 100, typical numbers. Okay, but in fact, you can even do even combine both of these approaches by taking this base factor and treating it as a test statistic in the frequentist approach, and then still compute its p-value. And this is the best possible test statistic that you could take, in the sense that it maximizes your probability of detecting true signal at a fixed false positive rate. Okay, so this is the approach that we will take here, and so to do these simulations, we will do then random walk without noise. These are null simulations. And then to compute the base factor, this is typically considered very expensive, and so it's hard to apply to large data sets. But in fact, in this case, it can be done very, very easily because our signal hypothesis is just a sinusoid. It just has a few parameters, period, phase, and the amplitude. And so there is no need to use MCMC algorithms such as nested sampling. You can just do Gaussian quadrature and do the integration directly. And for example, this will give you a base factor in around 30 seconds instead of several hours that the nested sampling would take. So now we can do this analysis. First, okay, before I move to the real analysis here, we did some statistical analysis. I show you the ROC curve. So this is the true positive probability as a function of false positive probability when we injected some signal in the data. And this is for various different test statistics. For example, if you take the Lomskargal periodogram score, this is what you get. And you can improve on that by using, for example, the base factor. Or this is just taking into account, which automatically takes into account the fact that the noise is then random walk, while Lomskargal periodogram assumes it's a white Gaussian noise. So for example, at some fixed false positive probability, say 10 to the minus 3, with Lomskargal periodogram, you have a pretty low chance of detecting a true signal. Whereas if you use the base factor, you will get about 20 times larger probability, which is now pretty decent. Okay, so now let's apply this to the actual data. So we analyze 30,000 quasars from the PTF data, and this is the distribution of the base factor that we get. This is the cumulative count. So these candidates here with very large base factors are our best candidates. Now we would like to assess their statistical significance. So okay, if we do a frequentist approach, we generate null simulations by assuming it's then random walk, and then we do 100 simulations of the entire quasar data set. We repeat the same analysis, and this is the median over these realizations that we get, and this is the 99th percentile. So if we were frequentists, now we would just look at these numbers here and these numbers here, and because this is much larger than this, we can claim that the p-value of this is much lower than 1%, and so these seem like very, very promising candidates. On the other hand, if we were Bayesianists, we would just look at the raw value of this base factor, which is here, log base factor is 25. So e to the 25 is a pretty large number, much larger than 100, even after you take into account that you did the multiplicity, because you looked at 30,000 different quasars, it's still a very large number. And so you would claim this as genuine signal detections. And this is essentially what Maria did in 2016, this approach, and this candidate looked very promising. But we're not very satisfied because while doing this, we assume that the noise is damped random walk, and this might not be a very good assumption. And both approaches will suffer if this is not true. For example, if in the frequentist approach, if our simulations are not correct, for example, if we took into account some more complicated systematics, these systematics could actually trigger much larger detections, and then our p-value would be much lower than 1%. On the other hand, in the Bayesian approach, we assume some form of the likelihood, which assumes then random walk. And if this is not true, then the base factor is also wrong, and in fact, it could be largely overestimated. So what we desire is a more robust data-driven way of assessing this statistical significance that will work directly on the data and therefore automatically include all the systematics which are present there. So this is where, okay, so a very simple approach that one can take is, for example, bootstrap. So here the idea is that you take the data and then you randomly reshuffle these data points and treat this as an effective simulation of the no signal hypothesis, because when you do this, you automatically destroy all periodic signal. But this approach is not really applicable in this case, because when you do this, you also reshuffle noise, which we know it's correlated. And so you will also destroy the noise features. Okay, so we cannot do this simple approach. but this is where our null signal template approach comes in. So here the idea is that instead of reshuffling the data, we will play with the template which we are looking for the data. So so here in this blue line is our periodic sinusoidal signal, and then we will take individual cycles of this sinusoid, and then we will randomly stretch or contract them. So the resulting template, which is now shown in this orange, is no longer periodic. It's completely made up, and it for sure doesn't describe anything physical. And we can design it by carefully doing this randomization of the periods, that its overlap with the original template is very small. So now if we apply this, now if we use this orange template to look for periodic signal, we will first for sure not pick up any periodic signal because we have made sure that the overlap is small. And second, because it looks kind of similar to the periodic template on short time scales, so time scales comparable to 1 period, it will trigger very similarly on noise. And the hope is that it will give us the same false positive distribution as if we were using the periodic template. And so then if these two things are true, then we can basically repeat our analysis with this modified template, and then this will act as an effective simulation of the null. So as if there was no signal, and then if we repeat this many times, we can get the p-value. So this acts as a simulation of the null, and it works directly on the data. It doesn't assume anything about the noise features or systematics, and so therefore it will automatically include all of those. Okay, so before we apply this to the real data, let me show you how this works in simulations. So here we perform the grid of different simulations. So we have different times. They're kind of similar to the PTF data, but they have different time sampling. So we have either uniform time sampling, then sampling with gaps, and then completely random time sampling. And we have different noise properties, either white Gaussian noise, Cauchy noise, so with very long tails, or correlated noise. But in all of those cases, when we constructed our model, we assumed that the noise is white Gaussian. So we were using long scalar periodogram score. We were pretending that we don't know what the actual noise is. And then we did our analysis with long scalar periodogram score. And this is the p-value that we get as a function of the score. So this is the cumulative distribution. And this is the black line is with the periodic template. And then we repeated the same analysis with the null signal template, which is now in this color. And now you can see that even though we knew nothing about the actual noise, the null signal template acts very similarly as the periodic template. In fact, these distributions are indistinguishable up to statistical fluctuations. And so because our noise model was pretty bad, our test statistic was not suited for this large tails, we got very large scores. And so if we just didn't have the null signal template, we would think, okay, these are very large scores compared to what we would get with white Gaussian noise, and so we can claim this as a discovery. But here now the null signal template tells us that it's actually nothing special, that even the null signal template is able to find these large scores. So we would assign these candidates low p-values, large p-values. And we would reject those discoveries. These were simulations all with just noise, so no signal injected. Now let's repeat the same now with injected noise, injected signal. So now we did everything the same, except that we inject some periodic signal. The black line is the reference line from the previous slide, so it's if there was no signal. And now the orange line is the analysis with the periodic template when there is injected signal. And you can see that it gives us much higher test statistic than the one without injected signal. So this is able to pick up the periodic signal that's present there. But then the blue line is the analysis with the injected signal, but with the null signal template. And now you can see that it doesn't pick it up. Instead, it gives us the distribution as if there was no signal. So now in this case, if this was actual analysis, we would see these test scores here, and we could compare them to the null signal template here, and we would see that the difference is very large, and we could claim this as significant discoveries because they are much above the null signal template results. Okay, now let's apply this to the actual data. So these three lines are from before. So we have the null simulations assuming 10 random walk and the analysis with the periodic template, but now we have added on the analysis with the null signal template. And now you can see here that the situation is actually the opposite of what we had on simulations with injected signal. So if there was some signal, then null signal template should not be able to pick it up. It should be lower than the blue line. And then we could claim this as discoveries. But what happened here is actually just the opposite. Now that the null signal template actually picks up more false positives than the periodic template. So what does this mean? Okay, first of all, it means that for sure we cannot claim that these are significant discoveries because there are more non-periodic features which trigger more. And second, that this damp random walk is clearly a very bad model for this noise because it was not able to model these features that showed up with the null signal template. So clearly there are some non-periodic features there. Yeah.
So when you build a null signal template, so when you stretch and squeeze the sinusoidal wave, is the way in which you squeeze and stretch anyhow informed by the data itself? So is it trained to resemble the data as much as possible?
No, it's completely random.
Okay.
It's
Okay.
just fixed in advance and it's always the same.
And still it picks up better than.
Yeah.
Okay.
Yeah. It's designed for very short periods. We designed it so that it doesn't overlap with sinusoid. But
So there's no fitting that you're doing.
No. It's fixed.
Okay.
It's fixed like the periodic template. It's fixed. Yeah.
Okay.
I mean, it has the same parameters as the periodic template, so it still has the parameter period and phase and the amplitude, but nothing more than that.
And I mean, there's a random parameter that you use for stretching and squeezing.
Yes, but this one is fixed.
Okay,
It's not
okay.
fitted. Yeah.
Okay, thanks.
For example, we say always the second period is twice as large as the first period, and the third period is always 1.3 times shorter than the first period, and so on.
For all the light curves?
For all the light curves, yeah. Okay. So so these are about the conclusions that we have about this search for supermassive black holes, and we have seen that this NST is a pretty robust way of assessing the statistical significance. So we would like to apply it more broadly. And so now the second analysis that I will talk about is search for exoplanet transits. So here we are. So here we'll be looking at Kepler Space Telescope data, which is okay. So we have time flux measurements of star over a period of around 4 years, and then the signature of the planet is that if the planet is aligned with our line of sight, when it goes in front of the star, it dims it, and we see this as a decrease in the brightness, which occurs periodically. So this black template here is what we would expect from a planet signature, and then we will construct in a very similar way a null signal template, which will be just shifting this location of this transient by a random amount, a fixed random amount, and then we will repeat the same analysis as we did with our periodic template, also with the null signal template, and it will act as a null relation. So now here we did this analysis for 5,000 randomly chosen Kepler stars, so for each of those stars we looked at planet candidates, compute their base factors, and then did some cutoffs and filtering, and these are then the candidates that remain, and so this is their distribution as a function of the period of the planet. Now the analysis with the periodic template is shown in black, this feature here, and you can see that it has some, so these are all false positives, and you can see that it has this feature of the period which coincides with the period of the Kepler Space Telescope, which is a very known source of false positives, because basically when the Kepler Space Telescope orbits Earth, it has these periodic modulations where the noise levels increase, and this happens kind of periodically, but not strictly periodically. And so this is what is the cause of those. And you can now see that if we did the same analysis with our null signal template, we get the same distribution, and including this peak here, and this is half of that peak. Now this can be compared to the state of the art. So in the standard Kepler analysis is that you do basically bootstrap to construct effective null simulations, just that you take chunks of data and then you reshuffle them. They call this scrambling. And this is now shown in this blue line. And you can see that blue line does not pick up these false positives, which is because when you do scrambling, you also destroy this kind of periodic noise features. And so this means that our null signal template is actually the best method for assessing reliably these false positive rates, especially at these periods here. And these periods here are very important because we're very interested in habitable Earth-like planets around sun-like stars, and periods like that around sun-like stars are in the habitable zone. So with this, we're able to assess their significance. Furthermore, this can show even more prominently on the other data sets like that came after Kepler, like TESS, where scrambling is in fact not even possible, and NST is still applicable. So this is our future work. Okay, but let's. So now we see that we have a reliable way of assessing this, and we would like to first recompute the occurrence rate of Earth-like planets and get better estimates. And second, also look at individual exoplanet candidates and then reject or confirm them based on our NST criterion. We will this talk I will just talk about the second one because the first one is more work. These are the known Kepler candidates. The size of the dot is the radius of the planet here. So one Earth radius, two Earth radii. And then shown as a function of the effective temperature of its host star and the installation flux that it receives. And so then this green area is the habitable zone, either with some conservative definition or a slightly broader definition. And so these candidates here are the most interesting because these are sun-like stars. There aren't a lot of candidates. And so it's very important to individually assess them. Because this will have a large impact on occurrence rate. And then the color of these candidates is the reliability that was assigned by Kepler doing scrambling. But actually, even worse, it was not applied on a star-by-star basis. It was applied on a population level. And so this is kind of like the average reliability, which is not as accurate. And now we did the same analysis with our null signal template, and now you can see that some of these colors change. For example, this candidate here was previously considered kind of reliable, but now is definitely not reliable. And on vice versa, for example, this candidate here was previously not strictly confirmed, but now we can claim that it's a pretty secure discovery. And for example, this is Kepler 452b, which is the most Earth-like planet in the habitable zone around sun-like star. So this is quite important. So yes. Okay, yeah. Yeah, so this wanted to say about exoplanets. Are there any questions about that? Yeah.
How many did you manage to exclude? Like I'm trying to read from the colors. Like from your analysis, how many?
So here around 45 candidates, and we confirmed at the end 30 or so. Yes, with some that were now below threshold and some that were previously below and now above. Okay, so now since we still have some time, I would also like to talk about some completely different topic, which is in our group we're also developing sampling methods. And I would like to briefly advertise those. I know that, in astronomy community, typically a kind of outdated sampling methods are typically used, for example, like random walk metropolis or EMCE. And these methods, although they work well in typically low dimensions, they do not scale very well to high dimensions, and they're not very efficient. So I would like to talk about two groups of methods. So in the first case, it's a gradient-free, where you cannot compute the gradient of your log likelihood. In this case, I'd like to emphasize the codes developed by Minas. Maybe you also know him. He's Greek. So this is preconditioned Monte Carlo, and it achieves pretty good results, much faster than, for example, nested sampling. And it can also give you the evidence and so on. It works on the basis that you could do Monte Carlo, but then the geometry of the target influences your speed of convergence a lot. So it does normalizing flow to simplify this geometry. And then in the other in the other setting where you can compute the gradient of your targets. This is so if you a lot of like legacy codes do not have gradients, but if you can afford to do a gradient, it pays off because the sampling will be much faster. And in this setting, no U-turn sampler, NUTS, is the state of the art. And it's a very decent method. It works very well, but it doesn't scale up to extremely high dimensions, like above 1 million parameters, because it has this decay of performance as d to the minus 1/4. In this setting, we also developed our own method, which equals microcanonical adjusted metropolis adjusted microcanonical sampler. This one performs about a factor of 2 to a factor of 7 better than NUTS, and it works on very similar principles. It just uses a different dynamics, which is more stable, but it has very similar limitations as NUTS. It has the same scaling to high dimensions and so on. So we also developed another method, which we call microcanonical Langevin Monte Carlo. This one does not include metropolis adjustments, so it doesn't have a decaying performance with high dimensions. And in fact, for many models, we can find that its efficiency does not drop as you increase the dimensionality. And then also, if you have parallel resources, you can speed up the convergence in terms of walk-out time by many orders of magnitude. And we have an ensemble version for this, where you run multiple short chains, and then each chain only collects one sample. So I would just like to show you some results on different benchmarks and also real problems. So on this left-hand side, we have this microcanonical Langevin Monte Carlo, and this is the height of this column is the efficiency of sampling. So how many effective samples do you get per some fixed computational time? And so, okay, these are Bayesian inference problems that are like in 50 dimensions and 2000 dimensions, so kind of low dimensional. Then we have some problems from statistical field theories, 5 to the 4 field theory, and then we have some real problems from cosmological field level inference. And you can see that in this now this MCLMC is compared to NUTS, which is considered the state of the art. And now you can see that in this low dimensional, you get a factor of efficiency of a few up to a factor of 10. But then in these high dimensional applications, the factor is much larger. For example, here it's already a factor of 60 times faster. And so, in fact, NUTS is prohibitively slow to be used for this kind of analysis, where MCMC is now still applicable. Here is also the convergence of the ensemble version. And you can see that this one is really fast in terms of number of iterations. So, for example, you want to sample from this banana-shaped black line here, and then your initial distribution of the particles. And then if you evolve them after 5 iterations, 10 iterations, and already after 20 gradient calls of the likelihood, your distribution is basically there. So you already have your posterior. So this is really fast. And now I'd also like to show you some results from other people who have applied MCLMC to very real problems in cosmology. So this is the cosmological field level inference from CMB lensing. And this is now as a function of how big your data set is. So this is you have a square grid, and this is from 64 squared to 500 squared. It's already around million dimensional. And so then the height of this column is how many effective samples do you get for some computational budget. And now the green one is MCLMC compared to HMC, which is the state of the art previously. And you can see, okay, in this low dimensional and this is the log scale, right? So in this low dimensional problem, HMC still kind of works, but it's much lower. But then in this high dimensional scales, it's already orders of magnitude faster to use MCLMC. And it's also compared to MUSE, which is in fact a much more approximation. It's basically a Laplace approximation. So linear methods. So so its scaling to high dimensional is pretty good, but it has some bias which is impossible to control. So it's not as reliable. So with this approach now we can actually use MCLMC for a lower computational budget and get higher precision. And this is also a similar analysis. This paper just came out this month. And they did a grid of different sampling methods and applied them to cosmological field level inference from the Galaxy service. And now here they show the number of gradient evaluations that you need to get to some accuracy. So the lower the better. This is also the log scale. And here you can see that, okay, now our MC is in green. And you can see that, okay, these are for cosmological parameters and for the field parameters. And you can see that now it's orders of magnitude faster than, and for example, NUTS. And this is our other method, which is metropolis adjusted. It's still better than NUTS, but doesn't really like include this kind of performance boosts. So yeah, I would like to stop here. Take questions.
This question, in your method for calculating the null, have you compared the Fourier spectrum of your null with actual observables to make sure that they have similar shapes?
So I didn't catch it. So the power spectrum of the
of your null with the actual data against the actual data to make sure that the noise has similar characteristics. Like you create your null,
yes,
based on your method. You calculate the Fourier spectrum of your null.
Of the null, yeah.
And also you calculate the Fourier spectrum of actual observed likers.
Yeah.
To make sure that the noise characteristics are similar.
Yeah. Okay. So the power spectrum of the periodic template is a delta function. It's because it's sinusoid, right?
But the scrambled one?
The scrambled one is a slightly broadened delta function.
Okay.
So it's like a broadened delta function, and then the data is typically look at the background, some dense random walks, or some power law decay, and then it has spikes, which you try to interpret as delta functions.
So then I'm surprised that you are getting so good results.
Why? When you fit for it, you take into account also the background.
So in your null spectrum, you add a noise component similar to the data?
Yeah. In both approaches, you have both the background and the signal.
Okay. So you add by hand the background?
Yes.
The noise?
I mean, you assume something about the noise, but you do this assumption the same in periodic analysis and in the other analysis.
Okay. So you don't simulate a full light curve from your periodic signal?
We don't do any simulations here, right? So in this case, we don't just take the actual data, you analyze it with the periodic, basically do the fits with the periodic template, taking into account the fact that the noise is correlated. And then you do the same with this non-periodic features, again, taking into account that noise is correlated. This assumption that noise is correlated is of course,
okay.
It's imperfect, but still a null signal template correctly.
I missed a bit. I mean, this is very impressive how your sampling method works so efficiently. How do you get this speed up?
Okay, I can show you. I can show you very briefly. Can I? I can show you. Are you familiar with Hamiltonian Monte Carlo?
Maybe you need to explain that.
Okay. So how to do sampling in very high dimensions is okay. In high dimensions, the probability mass concentrates on a single shell. It's called the typical set because and then everything that's not on this typical set is the constant or the surface of constant probability density, and everything that's not on this typical set contributes nothing to the expectation values. So the way you want to design your samplers is so that they move basically only on that typical set and not away from it. And so this explains very clearly why methods like random walk metropolis don't work well, because they just propose random directions. These random directions have basically zero overlap with these right directions along the typical set. And so they're always rejected unless the step size is very small. And so, okay, the idea behind Hamiltonian Monte Carlo and methods like this is that they introduce some momentum, and this momentum kind of forces them to orbit around the center, so move along this typical set. For example, in Hamiltonian Monte Carlo, this is achieved by, so you have your configuration space parameters X, then you introduce some momentum, and then you invent some Hamiltonian function and simulate the Hamiltonian dynamics with this Hamiltonian function. And this Hamiltonian dynamics will automatically conserve the energy. So it will always move on the surface of constant energy. And then you additionally have these momentum resamplings where you jump to a new energy level. And then this entire procedure is designed in such a way that it converges to this canonical distribution e to the minus Hamiltonian. And then, okay, now you know how to sample from this distribution. And then you just need to make sure that you chose this Hamiltonian in such a way that it's marginal. When you integrate out the momenta, it gives you P of x. And this gives you a condition for what kind of Hamiltonian function when you can have. And then the idea is just, okay, let's simulate the Hamiltonian dynamics with this Hamiltonian, do this momentum resamplings, and then collect the location of this particle at different times, and this will be our samples. And this is very efficient. Okay, but still it needs to equilibrate between different energy levels. And this equilibration can be slow. So our idea is basically, let's not do this momentum resamplings and just sample along a single energy level. And then, so we will not converge anymore to this canonical distribution. We will converge to the microcanonical distribution, so the delta function of that energy level. And then all we need to do is make sure that the marginal of this, again, is P of x. And again, this will give us a condition of Hamiltonian function. It will be a different one. And then we simulate the Hamiltonian dynamics. And this is much faster. I mean, it's faster because you don't need to equilibrate. It's more deterministic. So this is one important speed up. And the other, even more important for high dimensional applications, is that we don't do metropolis adjustment. So because, okay, in principle, this gives you the right distribution because you can choose this Hamiltonian analytically. But in practice, you have to numerically integrate these dynamics, and this introduces some bias. And you correct for this bias by treating this dynamics as a proposal in Metropolis-Hastings algorithm. And this Metropolis-Hastings algorithm has a problem because it involves basically a sum of the energy errors for all the parameters. And then as the number of parameters increases, this energy error grows, but you need to keep it fixed, otherwise your acceptance rate will go to 0. So you need to reduce the step size to compensate for that. And this gives you this decay in performance. Now, on the other hand, if you don't do that, you don't get a decay in performance, but then you have some bias in numerical discretizations. So we have basically invented a method which controls this bias to be always smaller than the variance. And then if you can do that, your bias is negligible and you don't have the decay in performance. That's the short answer.
Just to follow up. So is there a theorem that guarantees that actual real world data will always have these typical pixels that accumulate around? Or I mean, what guarantees that the parameter space is not filled, right, with pixels? Why do you have to have this subspace?
Oh, so so asking why we have a concentrated measure, why it's not just everywhere in the space, or
I mean, I mean, you said you assume that there is a typical right ensemble of pixels, right, and you want to orbit around them. But what guarantees that this will be the case with real world data? Is there a mathematical theorem that?
Yes, for this, yes, because okay, so your distribution needs to be normalizable. That's for sure, right? Your distribution that you sample from, its integral over all space must be 1.
Okay.
Right? And then when you have more and more parameters, you can look at, okay, you take samples from the distribution. Suppose you can take exact samples, and these samples, if they are distributed according to this P of x, they will have different values of P, right?
Yeah.
And these different values will, as there are more and more parameters, there is kind of a central limit theorem, which basically tells that they will concentrate around some value. It's called concentration of measure. It's a pretty general thing.
But the central limit theorem applies for measuring one single parameter, right? I mean, you measure multiple times, right? And you sample from the same distribution, and then you get this nice Gaussian due to the central limit theorem. But if you live in a 20-dimensional space, right? Then you are sampling from a vast, or if you're doing AI, right? And you have like 20 billion parameters, right? Then what guarantees that there is always going to be a subset of this humongous phase space, parameter space, that will actually be relevant, so that you can ignore the rest?
I mean, I have to think about how to explain this well, but specifically, for example, for neural networks, there are results like concentration of measure results, which show
I
this
know
type
it
of thing.
exists. I'm wondering why. I mean, is there an underlying theorem? I mean, is it, what does it mean? Why should natural data, right, with humongous parameter spaces be always in a subset, so that you can actually work? I mean, otherwise this method, none of this would work, right? And AI wouldn't exist, right? So, but why? Why does it work? I don't understand physically, right?
Okay, I will think about it.
Okay.
But yes, it's okay, I don't know.
Maybe if you think like one distribution has a peak and every distribution of every parameter has a peak, there is probably a part of the parameter space where all the peaks concentrate. Just can't wait.
Yeah, but there's no way. There's no
but
reason
it's
why
actually the other way around.
It's the other way.
None is on the peak. For example, if you take a standard Gaussian and you look at, okay, maybe you have a standard Gaussian and you want to compute expectation values with that standard Gaussian, and then you look at which points contribute to those expectation values. It's the points which are square root of d away from the origin. So the mode doesn't contribute at all, right? For high dimensions.
Yes, thank you for the great talk. I think I have a more physically motivated question, maybe. So I was curious about the results with the light curves for the two-dimensional black hole binaries. And so in practice, often what we observe is not anyway like an exact periodicity, but like something more that's like quasi-periodic. So because like especially AGN, like very messy systems, right? Like one accretion disk has an outburst, or like things can happen, right? So, and I assume if you were not to expect like a completely periodic template, but like something that's more quasi-periodic, it would not be as easy to distinguish, like for because in this case, the NST was like outperforming kind of the had higher probability than the periodic light curve, right? But if you have something that's more quasi-periodic, a little bit more messy, then this distinction will become less pronounced, right? Did you look at that?
No, we didn't, because I don't think there are any well-developed templates for this more complicated situations that they talk about, right? We just don't look what we're looking for, right? But I suppose if you had this kind of templates, you could still use them to construct null signal templates. For example, I don't know, if they have some quasi-periodicity, you could take this periodicity and stretch it. And then the next cycle and stretch it. Even though they're not all the same, you can still manipulate it to get something that you didn't get from numerical simulations, right?
Yes.
But I think it's a general problem for detecting this kind of features, right? There's just no well-developed template bank of things that we're looking for.
Also, in the case of the binary, you expect like the binary period to set the periodicity. So there, you could have other effects from the accretion disk, but if you have like a binary that sets the clock.
But even that is not strictly periodic, right?
I mean,
It's kind of.
There is a prominent feature.
Yeah.
It's not how you make these templates. It's like it's not that easy to make like a more realistic template.
Yeah.
I think